Okay, so we have a question. A question that tells me that I need to prove that we have an invertible matrix such that p minus 1 a to the power of np equals a certain matrix, which is this one. I need to prove that the matrix that was shown above, and I will show you, there is an invertible matrix such that it equals this one. And if you notice well, this is a Jordan form to the power of n with a Jordan block, or with eigenvalues of 1 and Jordan block of size of 3 and size of 1. So we start with this matrix and we need to find the Jordan form, and we need to find a to the power of n. So we start by trying to find the Jordan form, the eigenvalues, throughout the characteristic polynomial. This is how we do that. A minus lambda I, and taking the determinant of it will give you this one, and finally this one. So this is the characteristic polynomial. Y minus lambda to the power of 4. Now, I need to find the geometric multiplicity. I know the algebraic multiplicity is just the power of this in the characteristic polynomial, but what is the geometric multiplicity of this eigenvalue of 1? In order to do so, I will look on the related nilpotent matrix, let's call it, of A minus I. It will give me a nilpotent matrix. This nilpotent matrix, I can look on its dimensions, because I will use it, and when I look on the rank of this matrix, this nilpotent matrix, I will get that the rank is 2. Therefore, the dimension of the null space is n minus 2, which is 4 minus 2, which is 2. This is the dimension of the kernel of this nilpotent matrix n. For the corresponding eigenvalue 1. Now I can go on and continue with this nilpotent matrix and take it to the power of 2. We will use it and look again on the kernel, on the dimension of the kernel of n squared. When I'll do so, I will look on the rank. I can, for example, look on which columns are multiplicity of the other. You can see it right away. This, for example, this is 3 times this, and this is 6 times minus this. Okay, so the rank is 1. Therefore, the dimension of the kernel of this n squared is 3. Great. Now, if you go one step further and look on n cube, you will get zeros. It means that the rank is, of course, 0, and therefore the dimension of the kernel of this n cube is just n minus the rank, which is 4. Now I can use the formula that will tell me how many blocks of certain sizes, which is this formula. Okay, so if I look how many blocks are of size 1, what I do is take 2 times the dimension of kernel of n minus dimension of kernel of n to the power of, here is 1, so I take 1 minus 1, which is 0, n to the power of 0 is just the identity matrix, so dimension of kernel of I. And from this I reduce the dimension of kernel of what is here plus 1 to the power, what the power of here plus 1. So I have 1, which means that I have 1 block of size 1. For blocks of size 3, I can use the same formula. I take 2 times dimension of kernel of n squared, n cubed, minus dimension of kernel n to the power of size of 3, so 3 minus 1 minus dimension of kernel of n3 plus 1, which is 4. When I do that, and I know what is the dimension of kernel of n to the power 4, because if n to the power 3 is 0, this will also be 0. I mean, this is the 0 matrix, so the dimension of the kernel is 4, so here as well it will be 4. So this is also 1, so I have one block of size 3. Therefore, I have only eigenvalue 1, and I have two blocks, one size 1 and the other one size of 3. Therefore, this is the Jordan form. One block of size 3 and one block here of size 1, each of them for the eigenvalue of 1. Now this is the Jordan form for A. Let's look on Y. When we take p to the minus 1 A and P, we get to this one. Remember that for the Jordan form we found, we can just say that it's just the identity matrix plus a nilpotent matrix with 1 on the first superdiagonal. So I can just present the Jordan matrix as this sum of I and nilpotent matrix of J, where J is this one and I is the identity matrix. And I can of course calculate the powers, and note that for power of 3 or greater, it will be just the 0 vector. So I can just calculate j to the power of n by taking this I plus nj that we did and taking it to the power of n. This is the binom. Now I don't need all the binom. I need just until I get to n to the power of 3, so until n to the power of 2, because from this on, I'll just get zeros. So I take the first term in the binom, the second term, and the third. Now, why can I use the binom for this addition of matrices? Remember that it won't work for any matrices. You need that the matrices will commute in order for this binom to work. But a matrix with the identity matrix multiplication, of course, commute with each other, so we can use the binom. So here it is. We are finishing with this. We are taking just the first, second, and third term, and we are getting for this formula for the Jordan to the power of n. So I can take I, here it is, n nj, so n power of nj, and n minus 1 divided by 2 times nj squared, which will take the superdiagonal ones one further to here. Calculate it in, I will get j to the power of n. Adding them all together will bring me to this j to the power of n. Okay, I think that this is enough for now. This was a question in Jordan blocks and Jordan forms. I wish that was a little bit of help on how we work with Jordan forms a little bit. It was just an example, an exercise. And I need to thank you all for watching this and for Gemini for writing it down. Thank you all very much, and that's it for now.